It's not going to be particularly difficult, but it is a sort of introduction to a new type of bonding that we haven't talked about yet. And it's a bonding called a coordinate bond. Now, what a coordinate bond is, it's different from the usual bonds we've been looking at. When we have an ionic bond, you have a charge and a charge, and they're just brought together by attraction. When we have a covalent bond, we have sharing of electrons. Electrons from one atom are shared with electrons from another atom, and they create a bond. And that's a very strong bond. A coordinate bond is different in that just one of the partners brings the electrons. The other one doesn't bring any. And in this particular instance, it's water. It's the electrons and the oxygen of water that are involved in the bond. And they bond with the metal centers of the salt. And you also get the hydrogens basically forming a sort of hydrogen bond with the negative portion of the salt. And we call that a hydrate. So pretty much all salts will form hydrates, but only under certain conditions. So let's have a look and see what how the hydrate is described. So can everyone see my screen? I'm getting like a black screen. Can everyone see? Okay, thanks, Karina.
I can see it too.
Okay, yeah, it's weird. I'm getting just a black screen on mine. Just wanted to make sure everyone can see it properly. So a hydrate is a type of molecule which contains water, actually integrated right into the crystal. And we know that these interactions can be really, really strong. Think of it as an ion dipole interaction, because that's basically what we're seeing here. And it's the dipole that is bringing the electrons to interact with the ion. And this interaction is so strong that even when you crystallize this salt out of the water, some water even remains with the solid, and we call that a hydrate. And every salt has a particular formula for a hydrate. Not all of them are stable at room temperature. For instance, I was just reading this today because I found it interesting. Sodium chloride forms a hydrate. It forms a hydrate with 2 water molecules. However, the hydrate of sodium chloride is unstable at room temperature, and it breaks down. And so what we're going to be doing tonight is actually adding heat to an inorganic salt hydrate and basically driving the water off. Now, is that an exothermic reaction or an endothermic reaction?
Exo.
So is heat being released or is heat being absorbed? You see the reaction here. So we've got our hydrate and we're adding salt. We're adding heat to release the water as a gas. So when the heat is on the reactant side, is that an endothermic reaction or an exothermic reaction?
Endothermic.
Endothermic, that's right, because we have to add the heat in order to get this reaction to go. And so sodium chloride hydrate, dihydrate, does exist at low temperatures, like below, I think it's below -30. You can get it to form. So you actually like where the water is like really, really, really cold, like in Antarctica or something like that. If you get seawater to freeze, you'll actually see this hydrate. And I guess it has like really large planar type crystals. But we don't see it at room temperature because it's absorbed enough heat to release the water from the crystal. And so the salt that we get doesn't have any water in it. But the salt we're going to be dealing with tonight does. What salt are we going to be using? What's the salt we're going to be using tonight?
Epsom.
And what Epsom salt? That's right. What is Epsom salt? As I hear Googling going on in the background. Everyone's read this, right?
Magnesium sulfate.
Magnesium sulfate, right. So the example that's being given here is copper sulfate. And we've used copper sulfate in the lab. It's a beautiful blue color. And one of the interesting things about hydrates is that when you release the water, it changes the composition of the salt. And you can see that when we remove, hey, my lab assistant has joined us. When you release the water from copper sulfate, then the color changes. And it's because the colors come from the activity of the electrons in the metal. And so once you've removed those electrons from water, that changes the activity of the electrons in the metal and the color changes. So how we're going to do this particular reaction is just do exactly what's written here. We're going to take our solid magnesium sulfate in our example, add heat to it, and then we're going to see a mass, we're going to see a change in mass. Now the change in mass should be from the mass decreasing due to the mass of water being released. And the mass that's left over should be the mass of the anhydrous salt. What does anhydrous mean? When I say something is anhydrous, what does that refer to?
What is anhydrous?
Yeah, if I say a molecule is anhydrous, what does that mean?
No water.
It doesn't mean there's no water in it. And so you can buy these chemicals as the anhydrous form or the hydrate form. And speaking for myself anyway, we would much prefer having the hydrate form because it's really hard to get some of these chemicals, once you've driven all the water out, it's really hard to get them back into solution. If it's a hydrate crystal, that goes into solution like that. So it's much better prepared for putting in solution. So this gives you an example of the difference between a hydrate and the anhydrous form. So you can see on the right, you got these beautiful blue crystals of copper sulfate, copper 2 sulfate. Really, really pretty. We've seen those before. And then when you drive the water off, you can see basically we drive all the color off as well. It's still blue, but not nearly as much. And you can see that the
Last days of bakery.
bakery, I'll take some. And you can see the difference in crystals too. The hydrated crystals they're big and all fairly uniform in size. And when you remove the water, you sort of get this sort of flaky, sort of caked kind of look to it. And you'll see that when we do the experiment tonight. Well, the Epsom salt itself doesn't have any color. It's just a white crystal, but you see a big change. You get cold? You see a big change in what the crystals look like. So those of you that took the test, pretty much everybody, notice that when we give the formula for these, we also have to say how many water molecules are in it. And as I said before, these are all unique. Every salt has a distinct number of water molecules that are associated with it. And so we just use the very same nomenclature that we use for a lot of these: mono, di, tri, tetra, penta. Remember when we were naming covalent molecules, this was the nomenclature we used, and it's the same for water. So which one is so for the magnesium sulfate tonight, it's magnesium sulfate what? Which hydrate is it? You got a 1 in 10 chance if you're guessing. Oh dear, you're really cold. Oh. How many water molecules are associated with the magnesium sulfate? I guess it's not in the instructions, so I'll have to tell you. It's 7. So what will we call this? What do we call the whole molecule?
Magnesium sulfate heptahydrate.
Heptahydrate, that's right. So how are we going to do these calculations? So when you heat this salt, the first thing we're going to do is weigh it before it's been heated. So in this particular instance, the mass of copper sulfate was around 5 grams. And so you need to remember that in that is both the copper sulfate and the water that are present. And we don't know what the ratio is, for instance. So after heating, the final mass was 3.8 grams. And so the mass that was lost is 1.8 grams. And so we have to make the assumption that the mass that was lost is all due to water, because copper sulfate doesn't turn into a gas until several thousand degrees. And so we're not going to be playing with that kind of temperature tonight. It's going to be like a few hundred degrees, but that's going to be about it. So we have to assume that this is the mass of the water. So then we figure out how many moles of water is that. So we take our mass that's been lost, assume that's water, and turn it into moles of water using the molar mass of water. The other number, our mass that's left, now we have to assume that that's just copper sulfate. And we figure out how many moles of copper sulfate that is based on the molar mass of copper sulfate. So what we're looking for is what is the ratio of the moles of copper sulfate to the moles of water. And that's what the formula is. Remember, any formula we've ever looked at is based on moles, right? So if we know how many moles of copper sulfate there are, and we know how many moles of water there are, and we know what the ratio is, we should be able to say for every 1 mole of copper sulfate, there is X moles of water. So it's a fairly straightforward lab. The thing we have to look out for is two potential errors are, one, we don't heat it sufficiently. And so we don't drive off all the water. And so what that would do is decrease the number of moles of water and increase the number of moles of our anhydrous salt. So we would underestimate how many moles of water are there. The other error is that you'll notice that when we start to heat these, the crystals themselves actually start to pop, sort of like popcorn. And some of them might pop right out of the dish we're using. And that would decrease the number of moles of the anhydrous salt we're estimating is there, and increase the amount of water we think we're losing. And that would overestimate our molar volume of salt. So those are two things, or overestimate our molar volume or molar ratio of water. So that's two things we need to look out for. So when we do our moles of water to moles of magnesium sulfate, what we hope to get is an answer of around 7. Because if you look up the molecular formula for magnesium sulfate heptahydrate, you get, oops, let me go back, you get this. That's the formula. And you can see there's H14 in there, and there's no hydrogen in magnesium sulfate. So that's all from water. So if you got 14 hydrogens, that means you have 7 waters. And it's referred to as the heptahydrate. So the molar mass of anhydrous magnesium sulfate is 120.37. So we'll be using that. And the molar mass of water, you should know by now, is about 18 grams per mole. Use a more accurate number than that in your calculations. And then remember, use as many digits as you want in your calculations, and then figure out how many significant digits you should be reporting based on the accuracy of your masses. So, like I said, straightforward experiment. Hopefully everyone's got all these materials that just come nicely in one bag. One thing that you may not have that you'll distinctly need are the forceps, because I have burnt my fingers doing this stupid experiment in the past because I forgot to bring them. So have a pair of forceps, or if you don't have that, some gloves or just something that you can pull the aluminum weighing dish off of the wire stand. It's going to get hot. So not a very long procedure. So we're going to take 3 dishes, label them 1, 2, and 3. And then we're going to measure about 0.5 gram or so of Epsom salt. So you want between 0.3 and 0.8. Because that's sort of in the sweet spot of being able to drive all the water off in about a 10-minute period. If you have way more salt than that, it's going to take a lot longer to drive all the water off. And so you may underestimate how much water is actually there, because you may not have gotten rid of all of it. And too little, the difference in mass will be so small that you won't get a very accurate result. So the sweet spot for this experiment is around 0.5 gram, plus or minus like 0.2 grams. So get a very accurate mass. Remember to subtract the mass of the aluminum dish, and then we just heat it for 10 minutes. Take it off, let it cool back down to room temperature, and then take its mass and see what the loss is. And we're going to do that 3 times. So with your 3 different dishes. So this is just the basic setup. So the sterno can, I don't know if how many of you have been worked in the food industry, but you see these all the time, like under chafing dishes and heat trays and stuff like that. It's basically an alcoholic gel. And so when you light it, I think there's enough time. I think it'll burn for about 45 minutes or so. So you may use all of it, you may not. If it's still going, you can either just put the top back on the can and that will set the fire, let it burn out. You'll either let it burn out or just put the top back on it and it should extinguish the fire. It's a pretty colored fire, so you know it's kind of fun to just let that go. So then we're going to basically fill out our chart. So the mass of each dish, and then plus, so this would be before heating. Figure out what the hydrated mass of your salt is. And remember, this should be somewhere between 0.3 and 0.8 grams, and more accurate than that. So then the mass of the dish after heating and then letting it cool back down. And then you have the dehydrated mass, or what we would call the anhydrous mass. This should just be magnesium sulfate by itself. So if that is just magnesium sulfate, then you have a mass, you can figure out the number of moles of magnesium sulfate. The difference in mass between the hydrated and the dehydrated is the mass of water. With the mass of water, how many moles of water is that? So once you have your moles of magnesium sulfate and your moles of water, the ratio should be the formula for magnesium sulfate hydrate. So should be somewhere around 7. If you get a number like, you know, I think the first time I tried this experiment, I think I got like 4 or something. It was really bad. I think it was because I just didn't let it go long enough. So be careful with that. So any questions before we get started? You can see it's a fairly easy experiment tonight, but you're gonna have to be careful because we are dealing with fire. So make sure that you've got a space where, you know, nothing can burn. Don't have any, you know, big fuzzy bunnies or anything nearby. Any questions before we get going? Okay, so 5 minutes and we'll come back and get started, okay? All right, see you in 5. All right, so the first thing we're going to do is weigh out. Oh, we should get the mass of the pan, because we're actually going to,
Okay.
because we're not going to be removing the salt from the pan when we weigh it a second time. Oh, that's grains or ounces. So keep hitting that till you get to grams. Is that grams? No, that's grains. There you go.
Okay.
What do we got?
1.29 grams.
1.29 grams. Excellent. So you're going to want a final mass of around just a little bit less than 2. A little too much. You know, you don't need a lot. Perfect. 1.99. That's perfect. So we should have 2 significant digits in our mass. since we're dealing with less than 1 gram, and we've only got 2 digits on the scale past 0. So we should have two significant digits. All right, so let's take the top off of our.
Professor, for the mass with the salt,
Mhm.
I only got 1.36, so 0.6 grams. Should I be adding more salt than that?
You want your mass of salt to be between 0.3 and 0.8.
Okay,
So if the mass, so just calculate, ours was like around 1.3 grams. So somewhere around 2 grams would be perfect. I don't know
Okay.
how much, I assume that these aluminum dishes all weigh about the same.
okay.
There we go. Yes, you can see it's this really cool green color.
Hmm.
So that is, if you smell it, it basically smells like ethanol because that's what it is. It's a gel, yeah, nasty, right? It's a gel of ethanol.
Hmm.
Do you want to light it?
No.
No. Okay. There you go. You get
That's
this really
cool.
pretty blue flame.
Yeah.
All right. Put that over the top.
Then-
Yeah, see, try and spread the crystals out a little bit. So and just put it on. There we go. And we should set the timer for 10 minutes.
Oh. Starting to bubble.
Yeah, and you can actually hear. What do you hear, Raj?
Well, like popping.
Mm-hmm. Yeah, because it's actually boiling.
Yeah.
You wouldn't know it, but there's actually water inside there.
Yep.
And so one of the things I warn everyone about is, yeah, watch it carefully, because sometimes, like I said, like almost be like a kernel of popcorn, and you'll get a crystal that just pops right out. That's why we actually don't want to heat this too quickly. That's why we're using sterno rather than like a blowtorch or something.
Oh, cool.
So what's happening to the shape of the crystals, Raj?
They're expanding.
Mm.
Well, either that or they're just joining together.
But it definitely looks different, right? We don't see
Yeah.
those big
It's less
individual
grainy.
crystals are kind of like, yeah, melting together. Oh, turn that on.
Yeah.
Yeah, so there's a lot of waiting. Wrap up, and there's a banky there if you want to wrap up. Move this a little bit. Do you see any difference now?
The ones on the edges, I can't tell if it's just the light. They're looking kind of brown.
Mm-hmm.
And yeah, a lot less. I mean, on the edges, there's still small granules, but
You notice the crystals are also starting to get smaller.
Yeah.
You had this like big sort of melted mass in the middle, and now it's sort of starting to, little bits of it are starting to disappear. That's just the water being driven off.
Yeah.
Yeah, so we give it like another 7 minutes or so. And then we'll take the mass a second time. Hopefully all the water is gone. You gonna take that upstairs?
I mean, yeah, after the lab. It looks like the fire's dying down a bit.
It should, there's plenty of gel still in there.
Yeah.
Yeah. But yeah, pretty much all the sound now is just from the ethanol gel. I don't really hear anything from,
Mm,
our plate is really calmed down.
yeah. Yeah, we should put up the follow on this.
Oh, where is our
Hmm?
forceps?
Uh,
Oh, I took them. Need to move crystals around a little bit.
mm,
And you can see how dry they are
yeah,
now.
on the bottom, they're burning a bit.
Cassandra, you're back with us. All right. How you doing? Oh, really? Pretty short lab tonight, so. Did you get all the information you need, Cassandra? All right, sweet. You get these tiny little balls. You see those? Over here.
Oh, yeah.
Those must have been like just individual crystals.
Mhm. Yeah,
They didn't melt into each other like the ones in the middle did.
the larger crystals are starting to like deflate, I
Mhm.
guess.
Yeah, we've definitely noticed two different kinds of crystals here. There's sort of these individual ones that just got really small and kind of brown. I'm sure some of you have noticed those. And then the other ones that were sort of more together melted as the water turned from a solid to a liquid. Then they melted together and then it turned into a gas. So we got like 3 minutes. I don't know how much more these are going to change.
Hmm.
Right, so while you're watching this first one, you can go ahead and weigh out your second and third. Because we're going to be doing this 3 times. So it'll save you some time. So while the first one's cooling, you'll be heating the second one. While the second one's cooling, you'll be heating the third one. So we should have this whole thing done probably by 8:45, I would think. Does it look any different now, Raj, at all? It's pretty much staying the same.
Yeah, I mean, yeah, mostly staying the same. The bottoms are less burnt than I thought. They're just like grayish.
Mm-hmm.
Only on like the edges, but it gets really.
And we could be seeing some reaction between the magnesium and the aluminum. What's that?
The-
All right, so we're gonna need the scale again. Actually, we're gonna. So our 10 minutes is gonna be up. Then we'll just let it cool down for a couple minutes. We don't want to put something super hot on the,
Yeah.
especially since everything on there is made of plastic. Yes, you don't want to take your hot dish right off of here and put it on your plastic. Yeah, exactly. Because then it will be melted to it and you won't be able to get it off. Exactly.
Wait, heat melts?
Melts,
Stuff?
melts plastic.
What?
All right, you want to take that off?
Put it.
Just put it on the table. All right. We'll move this out of the way. So I'm just going to put the cap back on. And hopefully that will stop the fire. There we go. Yeah, so if you are going to do that, don't press it down because then, pressure is going to build up and it will pop. Just lay it down on top of it and then check to see if that put the fire out. No, apparently it has. So I'm just going to let that sit. All right, so we got 3 zeros there. All right, where's my pen? Oh, got it. All right, just give it another minute, and we'll get its mass. This should metals cool down pretty fast. They heat up very fast and they cool down very fast because they're metals. That's something that metals do.
Cool.
They conduct heat.
Wait, really?
Mm-hmm.
That reminds me of a really interesting science experiment where we
tested about which stuff conducts heat.
Mhm.
Surprisingly, we found out that wood doesn't conduct heat very well.
It doesn't.
Yeah. And neither does plastic.
Not very well, no.
And then the metals did, did pretty well in, heating stuff up.
All right.
That's what metals do.
Are you ready to take the mass?
Yeah.
Wait till that gets to zeros. There you go. And just put the whole thing right on there. What's our mass?
166.
1.66. Excellent. Okay, you want to stick around for the
No.
No, okay. All right. Thank you, Roger.
Actually, I'm just gonna take the jacket.
All right, I'm gonna move back and do the calculations.
Well,
So our original mass of the aluminum dish is 1.29 grams. Plus the hydrate, 1.99 grams. So we have 0.70 grams of hydrate. Our mass after heating was 1.65. So we lost So we lost 0.34 grams. That is our mass of water. And the amount that we have left is 0.36 grams. That is our mass of magnesium sulfate. So now it's just a matter, now that we know what the mass of our water is, and we know what the mass of our magnesium sulfate is, you should be able to figure out the molar ratios. I'll find. Okay. Let's clear this out. So I've got 0.34 grams of water. And I've got 0.36 grams magnesium sulfate. Now it's a strictly unit conversion, and we've done unit conversion since the class started. Hopefully we know how to do unit conversion from grams to moles at this point. So I want moles. So I'm going to put moles on top, and I'm going to put grams on the bottom. 1 mole of water is 18.02 grams. 1 mole of magnesium sulfate is 120.37 grams. Get rid of my grams. I've got moles. So 0.34 divided by 18.02 is 0.01887. Now, at this point, like I said, do not worry about significant digits yet, because we'll only do the significant digits when we get to the end of our calculations. I noticed that on the test that a lot of you, well, I don't know if it was you in particular, rounded their numbers in the middle of a calculation. And remember, we really shouldn't do that. So that's my moles of water. Now, what about my moles of magnesium? It's going to be embarrassing if I got a really crappy number. 0.002991 moles of magnesium. And so remember, what we're looking for is the ratio of magnesium and water. So I'm going to put water on the top, magnesium on the bottom, because there should be more magnesium. There should be more water than magnesium. And that'll give us our ratio. So 0.01887 divided by 0.002991 is my ratio of water to magnesium sulfate. Oh, not bad. So our ratio is 6.309, which is pretty good. I think I'll have to tell Roger, he'll be excited. So we got a ratio of 6.3. So we said two significant digits. So our final answer should be 6.3. And that's not bad. That is an error of only 9.9%. So that's pretty good. I'll definitely take that for working with only two significant digits and something that basically heats chafing dishes. So 6.3. So basically, like I was saying, anything greater than 5 is pretty good. You can tell he's a better chemist than I am, because the last time I did this, I got like 4. So he does a better job. One thing I did notice, when I was when he was taking the mass of the post-heated tray, the mass was changing slightly, and that could be that it was still warm enough that there may have been some water still evaporating. So you can see that we didn't get quite to 7. We got pretty close, but we didn't get quite to 7. So maybe a little more heating, or maybe if we'd broken up those larger crystals, we would have gotten closer, or even if we'd left it longer. So that is one thing you can do is you've got your 3 trays, take their mass within 2 or 3 minutes, and then maybe take their mask like 10 minutes later and see if it's changed. You may get some additional loss of water over time, even after you've removed it from the heat. So be on the lookout for that.